Hey there, science fans! Today we're diving into the fascinating world of the internet. It's a network of networks, all talking to each other. But how do they communicate? That's where TCP/IP comes in. Think of it like the internet's postal service. TCP/IP is a set of rules or protocols that govern how data travels online. It's like the rulebook for sending and receiving digital mail. IP, or Internet Protocol, is a crucial part of this system. It's responsible for addressing and delivering data packets, the little envelopes of information that zip around the internet. Just like your home address tells the postal service where to deliver your mail, IP addresses do the same for data packets. Every device connected to the internet has a unique IP address. This ensures that data reaches its intended destination. So next time you're surfing the web, remember TCP/IP and IP addresses. They're the unsung heroes working behind the scenes to connect us all. Now let's talk about those data packets. They're like the letters and packages we send through the mail, but in the digital world. When you send an email, watch a video, or even just browse a website, your data is broken down into these smaller packets. Think of it like this. Imagine trying to send a giant pizza through the mail in one piece. It would be messy and inefficient, right? Instead, you'd cut it into slices, pack them carefully, and send them off. That's what happens with data packets. They're manageable chunks of information that can be transmitted efficiently over the internet. Each packet contains a piece of the overall data, along with important information like the source and destination IP addresses. These packets travel across different networks and routers like little digital explorers until they reach their final destination. Once there, they're reassembled into the original data, just like putting those pizza slices back together. We've talked about packets, but sometimes even those packets need to be broken down further. That's where fragmentation comes in. It's like cutting those pizza slices into even smaller bites. Why do we need fragmentation? Well, different networks have different rules about the maximum size of data packets they can handle. It's like some mailboxes can only accept small envelopes, while others can handle larger packages. If a packet is too big for a particular network, it needs to be fragmented into smaller pieces. These fragments can then travel through the network and be reassembled at the other end. Fragmentation ensures that data can flow smoothly across networks with varying limitations. It's like having a universal adapter for your digital packages. Remember those different network size limits we talked about? They're determined by something called the Maximum Transmission Unit, or MTU. You can think of MTU as the traffic cop of the network, directing data packets based on their size. Each network has its own MTU, which defines the largest packet size it can transmit without fragmentation. If a packet exceeds the MTU, it gets pulled over by the traffic cop and has to be fragmented. MTU values can vary depending on the type of network. For example, Ethernet networks typically have a larger MTU than Wi-Fi networks. Understanding MTU is important because if packets are fragmented unnecessarily, it can lead to slower data transmission. Section 5. How fragmentation works, dividing and conquering data. So, how does this whole fragmentation process actually work? It's a bit like solving a jigsaw puzzle, but in reverse. When a device needs to send data over a network, it first checks the MTU of that network. If the data packet is smaller than the MTU, it's good to go and can be sent as is. However, if the packet is larger than the MTU, it needs to be fragmented. The original packet is divided into smaller fragments, each with its own header information. These headers are like the addresses and instructions on each envelope, telling the network where each fragment belongs and how to reassemble them. The fragments then travel independently across the network, like little data explorers, until they reach their destination. Section 6. Transparent fragmentation behind the scenes efficiency. Now there are two main types of fragmentation, transparent and non-transparent. Let's start with transparent fragmentation, which is like a well-oiled machine working behind the scenes. In transparent fragmentation, the fragmentation and reassembly processes happen at the network layer. This means that the sending and receiving devices don't even need to know about it. It's like sending a package and having the postal service handle all the sorting and repackaging at their facilities. You just drop off the package and it magically arrives at its destination. Transparent fragmentation is efficient because it reduces the workload on the sending and receiving devices. They don't need to worry about the nitty-gritty details of fragmentation. Section 7, Non-Transparent Fragmentation, a collaborative approach. On the other hand, we have non-transparent fragmentation, which is more of a team effort between the sending and receiving devices. In this case, the sending device is responsible for fragmenting the data and the receiving device handles the reassembly. It's like sending those pizza slices separately and having your friend put them back together into a pizza at their end. Non-transparent fragmentation requires more processing power from the devices involved, but it also offers more control over the fragmentation process. For example, the sending device can choose the optimal fragment size based on the network conditions. So, both transparent and non-transparent fragmentation have their pros and cons. The choice of which method to use depends on the specific network requirements. Section 8. Putting it together. An example of fragmentation in action. Let's say you're sending a large video file from your computer to your friend's phone. Your computer is connected to a high-speed Ethernet network with a large MTU, while your friend's phone is using a mobile network with a smaller MTU. When your computer sends the video file, it's broken down into packets. However, some of these packets are too large for your friend's mobile network. This is where fragmentation comes in. The network router responsible for connecting your network to your friend's mobile network will detect that the packets are too large. It will then fragment these packets into smaller fragments that can fit through the mobile network's MTU. Once the fragments reach your friend's phone, they're reassembled into the original packets, and finally, the complete video file is put back together. And that's how fragmentation ensures that even large files can be transmitted smoothly across networks with different limitations. Section 9. The pros and cons of fragmentation methods. Both transparent and non-transparent fragmentation have their advantages and disadvantages. Understanding these trade-offs can help us appreciate the complexities of network communication. Transparent fragmentation is generally more efficient because it offloads the fragmentation and reassembly tasks to the network layer. This reduces the processing burden on the sending and receiving devices, which can be especially beneficial for devices with limited resources. However, transparent fragmentation can also lead to increased latency or delay in data transmission. If a single fragment is lost, the entire packet needs to be retransmitted, which can slow things down. Non-transparent fragmentation, while requiring more processing power from the devices, offers more control over the fragmentation process. This can be advantageous in situations where optimizing fragment size for specific network conditions is crucial. For example, in wireless networks with fluctuating signal strength, adjusting fragment size dynamically can improve transmission reliability. Section 10. Fragmentation's impact, a key player in network performance. Fragmentation plays a crucial role in ensuring the smooth operation and efficiency of modern networks. By enabling data to be transmitted across networks with varying MTU sizes, fragmentation prevents bottlenecks and ensures that devices with different capabilities can communicate seamlessly. However, fragmentation also has its downsides. As we've seen, it can introduce latency, especially in cases where fragments are lost and need to be retransmitted. Excessive fragmentation can also put a strain on network resources and reduce overall network performance. Therefore, network administrators and engineers strive to optimize network configurations and minimize unnecessary fragmentation. Techniques like MTU discovery and proper network design can help reduce fragmentation and improve data transmission speeds. Section 11. Wrapping up IP fragmentation in a nutshell. So there you have it, an overview of IP fragmentation. We've explored how this essential process allows data to flow seamlessly across the vast and intricate landscape of the internet. From understanding the basics of TCP, IP, and IP addresses to diving into the intricacies of fragmentation methods, we've gained valuable insights into the inner workings of network communication. Remember, fragmentation is like the unsung hero of the internet, working tirelessly behind the scenes to ensure that we can send emails, stream videos, and connect with the world around us. So the next time you're online, take a moment to appreciate the magic of fragmentation.